So this is History of Mathematics, lecture 24. And May 20th, Monday morning, 8:30 in the morning is the final exam. And we're covering the last two chapters of the book on the work of the German mathematician Cantor. So in the text, this is chapters 11 and 12. It's on the general subject of set theory. And in particular, you're studying infinite numbers. So the fundamental definition is the following. Two sets, you can call them anything you like, A and B, S and T, X and Y. Let's say two sets, A and B, are equivalent, which means have the same number of elements. And this means have the same cardinality. If there exists a one-to-one correspondence, so this is an important definition, between A and B. And what is a one-to-one correspondence? A function f from A to B is a one-to-one correspondence if it satisfies the following two properties. First, f is one-to-one. And what this means is that if A and A prime are in A, and A is different from A prime, then f of A is different from f of A prime. In other words, if these are your two sets, A and B, and you have a function f between them, if you take two different elements, A and A prime in the set A, they get mapped to two different elements in the set B. So different elements in A get mapped to different elements in B. That's what it means for a function to be one-to-one. And second property, f is onto, which means for every element B in the set B, here's an element B, there exists an element A in the set A with f of A equal to B. So given an element B in A, there's always at least one element A in A such that f of A is equal to B. And these are really fundamental definitions, and you must know these definitions. Any questions about this? 1 second. Okay. And so just to review some simple examples. With sets E of positive even integers. And let's say call O the set of positive odd integers are equivalent because the function f from the even numbers to the odd numbers defined by f of n equals n minus 1 is a 1-to-1 correspondence. What is this function? Well, f of 2 is 2 minus 1 or 1. It's only defined on the even numbers. F of 4 is 4 minus 1 or 3. F of 6 is 6 minus 1 or 5. And in general, f of 2n is 2n minus 1. So every even number, so n even implies n minus 1 is odd. Everyone knows that. Subtract 1 from an even number, you get an odd number. And so this is a function from the even numbers to the odd numbers. It sends a positive even to a positive odd. Two different even numbers get sent to two different odd numbers. And every odd number, if you add 1, is an even number. So the sets E and the odds are equivalent. What's more interesting is, for example, let's look at an interesting set. So consider the set of lattice points in the first quadrant of the plane. So in the XY plane, this is the first quadrant, the upper right-hand corner, the upper right-hand quadrant. These are the points where all the coordinates are non-negative. And a lattice point is a point XY, where X and Y are integers. So what are the lattice points in the first quadrant? So we have 0, 0, 1, 0, 2, 0, sort of like this kind of checkerboard. You see 0, 1, 1, 1, 2, 1. So it's all the points where the coordinates are non-negative integers. And I claim, so let's call this, I'll use a Greek letter lambda. I claim this set of non-negative integral points in the plane lambda has the same cardinality as a set of positive integers, which is denoted by aleph naught. So in order to prove these two sets are equivalent, we have to show there's a one-to-one correspondence between the set of lattice points in this first quadrant and the set of the positive integers. Or another way of saying that is we must show lambda is countable. That is, there's a way to count off these points that puts them in one-to-one correspondence with the integers. Now, here's an example of what you should not do. Let's say we send this point to 0. This is the, sorry, 1. This is the first point. And suppose we call this the second, and this the third, and this the fourth. And we keep going along the x-axis. You can count off all the points on the x-axis, but then you'll never get to any of these points above the x-axis. So maybe a better thing to do is, let's say this is the first point. Let's say this is the second. We call this 2. And if you go up, let's call this 3. And then this be 4. And if you draw these diagonal lines, you can count off the lattice points in this first quadrant by going up each diagonal line and then to the next one. Like this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. In fact, what you'll see is, I mean, you eventually you hit every point, every lattice point, because every lattice point is on some diagonal. And if you go up these diagonals, counting off the points, you'll count every single lattice point in this first quadrant. So without giving a formula, and with a little bit of work, one can give a formula, but without giving a formula, one can still enumerate all the lattice points in this first quadrant. And that shows the set of lattice points is countable. And in a very similar way, you can show that the set, let me call it Q greater than 0. So Q stands for the rational numbers. So this is all strictly positive. Positive means strictly greater than 0. The set of all positive rational numbers. I mean, there are infinitely many of them. You have the integers, of course, but then you have all the other fractions, 11/3, 72 over 195. You have all these rational numbers. There are infinitely many, but it turns out there's a one-to-one correspondence between all the rational numbers, positive rational numbers, and the positive integers. We showed how to do that. It's also a similar diagonal construction. And just to go over for the third time, what is the great theorem in chapter 11? The way it's given is the set 0, 1. This is the open interval. This is all real numbers x, which are strictly between 0 and 1, is uncountable. And uncountable means not equivalent to the set of positive integers. There's no way to make a list of all the real numbers between 0 and 1. So there's a first one, a second one, and a third one, and so forth. And the proof uses what is called Cantor's diagonal argument. And the diagonal argument, and it's a proof by contradiction. So the proof by contradiction goes as follows. We start off by observing that every real number x between 0 and 1 has a decimal representation. You can write x as 0. Say A1, A2, A3, A4, and so forth, with the digits AI between 0 and 9, right? That's every number has a decimal. And the only time it's unique unless either you get zeros from some point on, an equals 0 for all n from some point on, n greater than or equal to n naught, or an is equal to 9 for all n from some point on. And in that case, we have something like this. You could have the number 0.2781 for 0, 0, 0, 0, 0, zeros forever. So this is zeros from some point on. Or this is the same as the number 2.781. Instead of 4 followed by zeros, 3 followed by nines. And if you understand what is a decimal representation of a number, then you can show these are exactly the same number. So to remove this possible ambiguity, let's say whenever we can represent a number in by two different decimals, and that only happens in this case, you have this eventually all zeros or all nines, always choose all zeros. So now every real number has a unique decimal representation. Any questions about this? This is basic. So let's assume this is a proof by contradiction. Assume the open interval 0, 1 is countable. That means we can enumerate all of the decimals. So in 0, 1. So we have x1, let's say, is 0. A11, A12, A13, A14, and so forth. And the next number in the list is 0.A21, A22, A23, A24, and so forth. And the next number in the list is 0.A31, A32, A33, A34, and so forth. And the next number is x4, 0.A41, A42, A43, A44, and so forth. And just keep going. The nth number in the list is 0.A N1, A N2, A N3, A N4, A N N plus 1, so forth forever. You have this long list of decimal digits. You have the decimal representations, and our hypothesis is that every x in the interval from 0 to 1 is equal to one of these numbers for some unique n in the positive integers. So our hypothesis is that this set of real numbers between 0 and 1 is countable, can be put in one-to-one correspondence with the integers, and here it is. This is the first, the second, the third, and so forth, the nth. Every number between 0 and 1 is on this list. And now we're going to construct a number y in 0, 1 that is not on the list. That is, y is different from xn for all n. And if I can do that, that will be a contradiction. It will contradict the assumption that every number from 0 to 1 is on this list. And what we do is we go down what you might call the main diagonal in this array of decimal digits. We have the first digit in the first row, or the first number, the second digit in the second row, the third digit in the third row, the fourth digit in the fourth row. In general, the nth digit in the nth row, right? So every one of these digits, every one of these decimals, it's an infinite decimal. It could be zeros or nines. Well, it could be zeros from some point on, but it's still infinite. And for the nth number in this list, we look at the nth digit. And we construct a number y, which will have digits b1, b2, b3, b4, bn, and so forth as follows. We choose the digit b1. Now we have 10 choices for every digit. The number is 0 through 9. Choose the digit b1, so it's not 0 or 9. And it's not the first digit in the first decimal. So for the first digit in the first decimal of the number y we're constructing, we choose a digit different from A11 and different from 0 to 9. So you have plenty of choices. Okay. Choose the digit B2 to be any digit, any number from 0 to 9, except 0, 9, and also the second digit in the second decimal. And in general, and this is the key idea of the proof, you choose the nth digit b sub n in this new number I'm constructing to be different from 0 and 9, and the nth digit in the nth number on this list. And I do this for all n. So I've constructed a number y, and it's a decimal digit. Every decimal digit represents a real number strictly between 0 and 1. It's not 0 because these can't all be 0. In fact, none of them is 0. It's not 1 because these are not all 9s. In fact, none of them is a 9. And here's the key thing. For all n, this number y is not equal to xn for all n, because every number has a unique decimal representation, and the nth digit of y is b sub n, the nth digit of xn is ann, and these are different. So y is different from xn for all n, and that contradicts the assumption that this list of x's, x1, x2, and so forth, contains every real number between 0 and 1. So this is Cantor's diagonal argument, and it is a truly beautiful and, in retrospect, very simple idea. But very often, simple ideas are brilliant. Okay. Any questions about this? This is, I keep going over this proof because it is so fundamental in modern mathematics. But it is, in many ways, the ideas are subtle, but the technical parts are very simple. Okay. Now, what about the sizes of this open interval from 0 to 1 and the whole real line? So here's the real line, R. So I have this whole real line, and on the real line, I have the open interval. How do those sets compare? Well, you might say there are more real numbers than there are real numbers between 0 and 1, and that's true. Because the set from 0 to 1 is a proper subset of R, but in fact, these have the same number of elements. So the cardinality of the real numbers from 0 to 1 and the cardinality of the real numbers are equal. And we call this C, because the real line is sometimes called the continuum. And we let C, the continuum, denote the number of real numbers. And how do I know these two sets are the same? Well, we already constructed a function from the open interval 0, 1 to the real numbers. The graph looks like this. This is a strictly increasing function. The value at a half is 0. As you approach 1 from the left, you're going out to infinity. As you approach 0 from the right, you're going to minus infinity. This is some function y equals f of x. And what that function is, well, we already studied that last week. The function f of x is 1 over 1 minus x minus 1 over x, which is 2x minus 1 over x minus x squared. This function, this is a one-to-one correspondence. This is a function from the open interval 0, 1 to the reals. If you take any number x between 0 and 1, this number, it's a real number, and as you go from 0 to 1, you're mapping the 0, 1 interval, the open unit interval, onto the real line. So R and C have the same number of elements. So again, the cardinality of the positive integers we denote by all of 0. The cardinality of the continuum of the real numbers we denote by C. And all of naught is not C. In fact, I want to say that the number of real numbers, all of naught, is strictly less than C. But to do that, I need to define inequality. So suppose we have two sets of sets, must define inequality. So suppose we have sets A and B, and I want to say, what does it mean for the set A to have strictly smaller cardinality than the set B? What does this mean? So we do it in two steps. First, we define less than or equal to. So we say the cardinality of A is less than or equal to the cardinality of B if there exists a function f from A to B that is 1-to-1. Not necessarily 1-to-1 and onto, but just 1-to-1. So for example, if I take the interval from 0 to 1 and the real line, if I define a function f from 0, 1 into r by f of x is just equal to x, this is 1-to-1. X is different from x prime, f of x is different from f of x prime. So this function is 1-to-1. So the number aleph naught is less than or equal to C, because the cardinality of the positive integers, sorry, that's not what I want to say. This is true, but it's not what I want to say. I want to define a function from the positive integers into the interval from 0 to 1. And I'm going to define that by, if I take any positive integer n, that f of n be 1 over n. So if n is a positive integer, 1 over n is a fraction, a number, between 0 and 1. So the cardinality of the positive integers is less than or equal to the cardinality of this open interval, where aleph naught is less than or equal to C. So this is what it means for one set to have less than or equal to the number of elements in another set. And we say that a set A is strictly less than set B in size if the cardinality of A is less than or equal to the cardinality of B, and they're not equal. So this is just what we say with real numbers, right? 3 is less than 5 because 3 is less than or equal to 5 and 3 is different from 5. So a set A is less than a set B in size if the number of elements in A, the cardinality of A, is less than or equal to the cardinality of B and not equal to it. So we already proved aleph naught is not equal to C. This was the great theorem that we just proved. There's no 1-to-1 correspondence between the positive integers and the real numbers between 0 and 1. So if aleph naught is less than or equal to C, and if aleph naught is not equal to C, then this means that Aleph naught is strictly less than C. So we have two infinite numbers, if you like. We have Aleph naught, which is the number of positive integers, and C, which is the number of real numbers. And Aleph naught is different from C. In fact, it's strictly less than C. So we can conclude from that that there are at least two infinite numbers. There are at least two infinite numbers, Aleph naught and C. Are there any more? No. Are there? These are just some questions that are natural to ask at this point. Are there more than two infinite numbers? Are there maybe infinitely many infinite numbers? Is there a largest infinite number? That is there some infinite number which is so huge, so infinite, that is bigger than every other infinite number? So is there a largest infinite number? Or, this is another possibility, given some infinite number, is there always a strictly larger infinite number? So, for example, we had the number Aleph naught, but then we found an infinite number C bigger than Aleph naught. Is there a number bigger than C? That is, given some infinite number, is there always one which is strictly bigger? If the answer to this question is yes, then are there more than two infinite numbers? The answer to that would be no. Are there infinitely many infinite numbers? The answer to that would be yes, because take a number and then there's a bigger infinite number. And then there's an infinite number bigger than that, and continuing that forever, you would get infinitely many infinite numbers. In particular, is there a largest infinite number? The answer would be no. Because given this presumptive largest infinite number, you can construct a bigger one. So these questions are answered in chapter 12. So in chapter 12, the grade theorem says that given any infinite number, there is in fact a strictly larger infinite number. So chapter 12 says the answer to this question, given some infinite number, is there always a strictly larger infinite number? The answer to that question is going to be yes. And the way we're going to prove this is as follows. So we will prove, given any set A, finite or infinite, there is a set B such that the number of elements in A is strictly less than the number of elements in B. So we're going to prove that given any set A, there is always a set B which has strictly more elements than A in the set of equivalents of numbers. And the set B is going to be what is called the power set of A. So let me define the power set of a set. So the power set of a set A is the set of all subsets of A. And it's denoted by a script B for power set of A. So let's look at some examples. Suppose I take A to be the set that just consists of one element, let's say the number 1. So what are the subsets of A? So first of all, there is the empty set, which is always denoted by a symbol that looks like this, which is the set that contains nothing. There's nothing in the set. And so for every set A, the empty set is a subset of A, always. It's a sort of figure. So the empty set is always in the power set of A. These are two sort of basic remarks. Also, every set A is a subset of itself. So A is in the power set of A. So if you take any non-empty set A, its power set always includes itself, the set A, and the empty set. So if I take A to be the set consisting of 0 and 1, power set of A, it always contains the empty set, it always contains itself, and there's nothing else it could contain that is just 1. So the power set, so the cardinality of A is 1, and the cardinality of the power set of A bar is 1, cardinality of the power set of A is 2. Suppose I take A to be the set consisting of the numbers 1 and 2. What are the subsets of A? I have the empty set, the set that just contains 1, the set that just contains 2, and the set that contains 1 and 2, which is A itself. And these are the only subsets of A, and these are all the subsets of A. And the number of different elements in this power set, 1, 2, 3, 4. So we have the cardinality of A is 2, and the cardinality of the power set, we use bars instead of signs. So in this first example, the cardinality of A was 1, and the cardinality of the power set was 2. In this example, cardinality of A is 2, and the cardinality of the power set of A is 4. Suppose I take a set with 3 elements. And it doesn't matter what I name the elements, 1, 2, 3, X, Y, Z, cat, dog, bird, 2, 3. What are the subsets of this 3-element set? There's going to be a lot more of them. We have the empty set. We have all the sets that contain just one element. So the set containing just 1, the set containing just 2, the set containing just 3. Then we have all the sets containing 2 elements. 1 and 2, 1 and 3, 1 and 4, and then the sets containing 3 elements, which is just the whole set. So if I count the number of elements that is sets in the power set of A, we have 1, 2, 3, 4, 5, 6, 7, 8. So when the cardinality of A is 3, the power set of A has 8 elements. In fact, you might notice 2 is 2 to the first power. 4 is 2 squared. 8 is 2 cubed. And in general, if A is finite, a finite set, and the number of elements of A in A is n, then the number of elements in the power set of A is 2 to the n. Of course, it's easy to observe that n is strictly less than 2 to the n. 1 is less than 2, 2 is less than 4, 3 is less than 8, 4 is less than 16. And you might ask yourself, why is this true? I mean, is it true? The answer is yes. This is a theorem. And maybe, since this is easier than the great theorem, I should at least prove this. Start by proving this. So let me just state this as a theorem. If the cardinality of the set A is n, then the cardinality of the set P of A is 2 to the n for all positive integers n. So there are many different ways to prove this. Let me give a proof by induction on n. Normally, you can start with 1. You can even start with n equals 0. Let's just look at it. N equals 0. That means the cardinality of A is 0. That means A contains nothing. So A can only be the empty set. And what is the power set of A? The only set in the power set of A is the empty set. So the power set of A contains one element, 1, which you'll notice is 2 to the 0. So when n is 0, the power set has 2 to the 0 elements. So this statement is true for n equals 0. For n equal 1, we already proved that if A is 1 element, then the power set of A has 2 elements, which is 2 to the first. And we already proved that if A has 2 elements, then the power set of A has 4 elements, which is 2 squared. And we already proved that if n is equal to 3, that is, if the cardinality of A is 3, then the power set of A has 8 elements, which is 2 cubed. So assume, so this is the inductive hypothesis. We assume this theorem is true for a set with n elements, and we want to prove it for a set with n plus 1 elements. So assume if you have any set with n elements, then the power set of A contains 2 to the n elements. And I must show that if the set A has n plus 1 elements, then the power set of A has 2 to the n plus 1 elements. This is what I want to show. So suppose we let A be the set consisting of the first n plus 1 integers. Probably a good piece of paper. This is makes more than just put it, just do that down. Suppose A is a set of the first n plus 1 integers. So let's partition the power set P of A into two subsets. Let's say P of A is going to be B1 union B2, where B1 and B2 have no elements in common. So I have P of A is the union of these two sets, and these two sets are disjoint. That means they have nothing in common. So if this is P of A, I'm going to divide it into two pieces, B1 and B2. So B1 is going to be all subsets of A that do not contain the number n plus 1. If you take a subset of A, it may or may not contain A plus 1. So let B1 be all the subsets that do not contain A plus 1. And B be all subsets of A that do contain n plus 1. So clearly, every subset of A either contains n plus 1 or it doesn't. And if it doesn't contain n plus 1, it's here. And if it does contain n plus 1, it's here. So if S is in B1, that is, if the number n plus 1 is not in the subset S, then in fact, S is contained in the numbers from 1 to n. Because S is a subset of the numbers from 1 to n plus 1, but it doesn't contain n plus 1. So S is a subset of the numbers from 1 to n. In fact, I could say this. If S is in B1, a subset, if S is in B1, so S is a subset, this is in the power set of A, subset of A. It's in B1 if and only if it doesn't contain n plus 1. And a subset doesn't contain n plus 1 if and only if it's actually a subset of the integers from 1 to n. So that B1 is in fact the power set of the set of integers from 1 to n. So the cardinality of B1 is the cardinality of the power set of integers, power set of the first n integers, which by the induction hypothesis is 2 to the n. So the cardinality of B1 is 2 to the n. These are the sets in here. If S is in, so then we can also say, let's look at how many elements are in B2. So S is in B2 if and only if n plus 1 is in S. So that means S is n plus 1 union, let's say S prime. S prime is in B2 if and only if n plus 1 is in S prime. So S prime is n plus 1 together with other stuff S, where S is a subset of the integers from 1 to n. If you take any set from subset of 1 to n and add n plus 1, that gives you the set S prime, which is in B2. And how many sets S can you pick? Power set of n of them. So the cardinality of B2 is equal to the cardinality of the power set of n. Which is 2 to the n. So I've taken the power set of A, I write it as a union of two disjoint pieces. What can we say? Number of elements in the power set of A is the number of elements in B1 plus the number of elements in B2. That's 2 to the n plus 2 to the n, which is 2 to the n plus 1. That's the proof. If I take a set with n plus 1 elements, every subset either contains n plus 1 or does not. If it does not, it's a subset of the integers from 1 to n, of which there are 2 to the n of them. If it does contain n plus 1, then it's n plus 1 union with a subset of the integers from 1 to n. So there are 2 to the n of them. And 2 to the n plus 2 to the n is 2 times 2 to the n, which is 2 to the n plus 1. So that's the proof. Okay. So this is the theorem about finite sets. But the great theorem in chapter 12 says that, so this is the great theorem in chapter 12 says that this is true for every set. And not just finite sets, but for every set A. So the theorem says that if A is any set, finite or infinite, then the cardinality of A is strictly less than the cardinality of the power set of A. So we have, for example, Aleph naught is strictly smaller than the cardinality of the continuum, C. Or let's put it this way. Cardinality of the continuum is the cardinality of the set of real numbers. This is going to be strictly smaller than the power set of the real numbers. So this is an infinite number bigger than C. And this will be less than the power set of the power set. And this will be less than the power set of the power set of the power set. So forever. So starting with any infinite set, take its power set, take the power set of that, take the power set of that. You get this infinite increasing sequence of sets whose cardinal numbers, whose cardinality or whose sizes are getting strictly bigger and bigger and bigger. So how do we prove this? So let's recall the cardinality of A is strictly less than the cardinality of the power set of A if cardinality of A is less than or equal to the power set of A, and the cardinality of A is not equal to the power set of A. So definition of inequality, one set is strictly smaller than another set if the first set has a number of elements less than or equal to the number in the second, but it's not equal to that. So we have to show, in order to prove strict inequality, we have to show two different things. Now, the first is easy to show. Because we have to define a function f from A to the power set of A that is 1 to 1. Right, to show that the size of a set A is less than or equal to the size of another set, in this case the power set of A, means there's a 1-to-1 function from A to P of A. So define this function by f of the element little a is just the subset of A consisting of the one element A itself. So this one element A, subset of A it's a subset of A, it's in the power set of A. So you send every element of A to the one element set containing A. And that's a 1-to-1 function. And that proves, therefore, the size of A is less than or equal to the size of the power set of A. We must prove, this is the hard part, the size of A is different from the size of the power set of A. And the proof is, again, by contradiction. If the cardinality of A was equal to the cardinality of P of A, then there exists a function f from A to the power set of A that is 1-to-1 and onto. That is a 1-to-1 correspondence. So suppose we have this function. That is, we're going to assume there exists this function from A to the power set of A, which is a 1-to-1 correspondence. So suppose the element A in the set A corresponds to some subset, say B and C. A is an A. This is a subset in power set of A. Let's say the element B corresponds to the set consisting of just one element. This is just a make-it-up example so you get some idea of the logic of the P. Suppose C corresponds to the set A, B, C, D. Suppose D corresponds to the empty set. Suppose E corresponds to the whole set A. Suppose F corresponds to the subset, some subset containing A, C, F, G, and so forth. Suppose G corresponds to the subset B, I, J. So we have some function F that sends every element of A, here are elements of A, and it gets mapped to some subset of A. And we assume this is a one-to-one correspondence. We'll show this is impossible. So we're assuming that for every subset of A, there's some element H that corresponds to that subset. I want to show that's impossible. So I have to construct, not necessarily I must construct, but I will construct a set B contained in A such that B equal to some f of H, this is my function F, is false. I want to show I can always construct a subset B that's not on this list. As I go through the elements of A, I have associated subsets of A, and I'm claiming that every subset of A is in this list, but I'm about to construct a subset of A that's not on this list. And this is an extremely fantastically clever idea. Let B be the set. So if I take any element X, X is mapped to some subset f of X contained in A. So here I have an element of A, and here I have a subset of A. And the two possibilities, just note, for all X in A, either X is in f of X. So for example, here C, and f of C is the set. This is my f of C. And notice that C is in f of C. On the other hand, here A is sent to the set BC. And so this is my f of A. And A, in this example, A is not in f of A. Here, C is in f of C. And those are the only two possibilities. For every element X in the set A, either X is in f of A or X is not in f of X. So either X is in f of X or X is not in f of X. And let B be the set of all X in A such that X is not in f of X. So B is a subset of A. It consists of all those elements of A with the property that X is not in the subset f of X. So B is an element of the power set of A. So I have given a perfectly valid definition of the power set of a set, and in that power set of the set A, I've given a perfectly valid definition of a certain subset. If this is a one-to-one correspondence, if this function f from A to the power set of A is a one-to-one correspondence, then there exists an element y in A such that f of y is equal to B. I've constructed this set B, and if this is a one-to-one correspondence, there's some element y that corresponds to the set B. So let me just summarize or repeat this because it's so fundamental. Assume there's a one-to-one correspondence f from the set A to the power set of A. That B be the set of all elements of A, x and A, such that x is not in f of x. So this is in the power set of A. If f is a one-to-one correspondence, then there must exist an element y in the set A such that f of y is equal to B. So the subset of A associated with y is the subset B. Okay? So we have an element y in it. And there are only two cases that we can consider. Either y is in the subset B, or y is not in B. One or the other happens. If you have set A, the subset B, and an element y, either y is not in B or y is in B. There are only two cases. So B is a subset of A, y is an element of A, and either y is in B or y is not in B. Let's look at this case first. In case one. Suppose y is not in B. That means y is not in f of y. If f of y is equal to B. But if y is not in f of y, then y is in B. And that's a contradiction. It says that if y is not in B, then y is in B. Well, that's absurd. So case one is impossible. What about case two? Suppose y is in B. But again, B is f of y. That means y is in f of y. But if y is in f of y, then y is not in B. Because B is all the elements y such that y is not in f of y. If y is in f of y, it's not in B. So if y is in B, then y is not in B. That's a contradiction. But these are the only two possibilities. Either y is, if there's a one-to-one correspondence, F, and if you take an element, you construct this set B, then there's an element y such that f of y equals b. If you assume y is not in B, you get a contradiction. If you assume y is in B, you get a contradiction. But these are the only two possibilities. So therefore, the assumption is false. There does not exist this f from A to the power set of A that's a one-to-one correspondence. Doesn't exist. So the cardinality of A is not equal to the cardinality of the power set of A. But we know that the cardinality of A is less than or equal to the cardinality of the power set of A. So this means that the cardinality of A is strictly less than the cardinality of the power set of A. And that is the proof of the theorem. That's it. So given any infinite set, there always exists another infinite set whose cardinality is strictly bigger than the set you started with. So given any infinite number, there's a bigger infinite number. And there's a number bigger than that. Bigger than that, you get this strictly increasing sequence of infinities, one strictly less than the next. That's the great thing. Any questions about this? In fact, so we know two explicit infinite numbers. We have Aleph naught, which is the cardinality of the positive integers, and C, which is the cardinality of the real numbers. And we know that Aleph naught is strictly smaller than C. And Cantor asked the following question. Does there exist an infinite number, I'll call it Aleph 1, such that Aleph naught is less than Aleph 1, strictly less than Aleph 1, and Aleph 1 is strictly less than C. And Cantor believed, but could not prove, that the answer was no. There's no infinite number bigger than the set of positive integers, strictly, and strictly smaller than the set of all real numbers. And this was called the continuum hypothesis. So the continuum hypothesis says that the answer to this question is no. There's no infinite number in between the cardinal numbers, the sizes of the integers and the reals. But he couldn't prove it. And one of the great results of the 20th century was an Austrian mathematician, Kurt Gödel. So in German, some letters have kind of accents over them. This is a double dot. Kurt Gödel proved that there are some statements in mathematics that are true but can't be proved. Now, you might ask yourself, what does it mean to say that a statement could be true but not provable? But that can be made very precise. And he proved that some statements are true but not provable. And Gödel and much later, a mathematician named Paul Cohen proved that the continuum hypothesis, usually abbreviated as CH is, if it's true, it's unprovable. So it's impossible to prove in ordinary mathematics that the continuum hypothesis is true, and it's impossible to prove that it's false. So this is one of the great achievements of the 20th century. Gödel proved actually several things. One is there do exist statements that are true but not provable. And he, together with Paul Cohen, separately about 40, 50 years apart, Gödel proved one part and Cohen proved the second, the rest. The continuum hypothesis is an unprovable mathematical statement in ordinary mathematics. This is one of the amazing discoveries of the 20th century. Of course, we're in the 21st century, so the 20th century is already getting pretty old. That's where we are. And with this, I might say, we've reached the end of the course. So we've covered all of William Dunham's book. Journey Through Genius. And every time I look at this book, my opinion of it gets better and better. This is the great theorem in chapter 12. So I think next week, Monday and Wednesday, will be devoted to like reviewing everything for the whole course. And there will be one more homework assignment on chapter 12. And I'll also, over the weekend, put together a review for the final. So the last two chapters are on the work of the 19th century mathematician Cantor. And the two great theorems.
Did you upload it?
Sorry?
Homework 12?
I'm sorry, I can't hear what you're saying.
Did you upload the homework 12?
I did not yet put together the homework assignment for chapter 12.
Okay.
So the homework assignments for the first 11 chapters are, that's what you've been doing, but there'll be one more homework for chapter 12. And I'll have that up in probably tomorrow, maybe tonight. And then over before Monday, I'll have a review. And both classes on Monday will be reviewed. I'll certainly review Cantor's work, because this is these are the two chapters that were not covered on the first or second midterms, but I'll also talk about everything in the course so far. And more important, I think, you can ask me any questions you might have about anything we've studied this semester. And let's see, It's supposed to be a beautiful day today, the temperature in the 80s, so hope you get a chance to enjoy the day. Any questions before we quit for the morning? Again, I remind you, I have office hour tonight at 7, and not, I'll see you Monday morning. Bye all.